Good afternoon everyone, and today I am going to talk about the exactly solvable spin liquids in Kittev bilayers and Moiré superlattices. So you have already heard a lot about PO 2D and 3D. Now it is completely bilayer. So just a very brief introduction. So when I am talking about spin liquids, so definitely something is solid and something is gas, and in that context I can tell that the magnet is kind of spin solids and the paramagnet is kind of spin gas, and spin liquid lies in between them, which is kind of a magnetic liquid where there is no order parameter exist, but some correlations between the spins are present. And in this context, in general, the interacting spin problems are very difficult to solve because of its numerical computational limitations. But if we can solve it exactly, then it gives us a very beautiful analytical insights what is happening within. And in this regard, Kittev model is very successful. So if you compare the two models in the right hand side and left hand side, you can see that in the Hamiltonian, in the left hand side, the Kittev Hamiltonian is bond dependent. So there are three coordination number is 3, and along with the 3 bonds we can associate 3 different spin interactions by Pauli matrices. And if we do this, then Kittev showed that we can decompose the spin in terms of the Majorana fermions, and this can be solved exactly by a beautiful reduced Majorana hopping problems where Uij is a very special operator. Which kind of operator is it? You can see that u square equals to 1, that means along each and every link the u can take only 2 values, plus and minus 1. This is called a link operator, and this also commutes with the Hamiltonian, that means it is a conserved quantity. So this we call about the Z2 gauge field. However, this is not a gauge invariant quantity, but we can define some gauge invariant quantity from here, which is the placket operator, which is the multiplication of all the Uij's throughout the plackets. Hence, so this also is a conserved quantity of the Hamiltonian. So if we can identify for which placket values throughout the lattices my system has the ground state, then I am done. And in this regard, for the Kittev model, it shows that for all the plackets, the placket values are 1, that means it is a flux-free ground state. So a conventional choice is taking all the link operators to be 1, and then it is a very easy problem which can be solved exactly by the simple Majorana hopping problems. Now our motivation is little bigger. We want similar models but in the bilayer regime. But now there is a problem. The problem is now I have 4 bonds. So my coordination number is 4. So I need to incorporate the higher dimensional algebra here, and in this regard I can associate 4 gamma matrices instead of the Pauli matrix. So this is a 4 cross 4 matrix. First 3 is the gamma 1, gamma 2, gamma 3, and the entire bond is at gamma 4. So you can think of this is kind of a spin and orbital, both degrees of freedom are present within the systems, or also you can think of the spin multiple operators. And if we use the similar algebra as Kittev did, we can see again we can decompose the same Hamiltonian in a very beautiful exactly solvable models. However, there are 2 Majorana fermions now present within the systems which starts talking with each other in presence of an external magnetic field, and even then it is an exactly solvable model. So again we need to define our placket operators. There are 2 types of placket operator. One is the intra-layer placket and another is the inter-layer placket, square placket and the honeycomb placket, and the placket operators define the link operators multiplication throughout the lattices. And if we do this, we get a very beautiful phase diagram of the flux crystals, where by changing the inter-layer coupling strength and the external field, we can get different flux crystals. So the first index is my intra-layer index, that is a 0, and the second index is my inter-layer index. So what this implies, so the first, if you see the last, the two-third phase, then you can see that the first 2/3 means that 2/3 of my honeycomb is in the -1 phase, and for the second 2/3 of my square inter-layer plackets are in the pi flux phase. So, and you can also see that a different gapped and gapless phases emerges within the systems, also with the quadratic band touching. Now again we are interested in more exotic situations. We have seen that this is a 0 pi sector, and now what if how this 0 pi phase evolves if we twist these bilayers. Now if we twist these bilayers, the intra-layer is still now same, but inter-layer will change. And how it will change? Now at each and every side the interlar bond distance will vary, and as the interlar bond distance will vary, so we can see that as the bond length increases, the coupling strength decreases, and we proved it by the exponential functions where r is the lateral shift. But along with this, I also introduced a cutoff on this, and you can see that if we why I have introduced this cutoff, because for my interior bonds you can see that two situations, the blue is the bottom and the above is the top. You can see can be certain cases where the bottom and top may be connected by two interior bonds, but that is the problem. We always want that every side should have at most one interior bonds similar to the bilayers, and so we have imposed this cutoff and neglected all the weaker couplings from this bilayer. And if we do this, then our model is exactly solvable, and if we impose this constant in the Monte Carlo, we can see very beautiful phase diagrams. And this is a very beautiful in the sense because this is a general phase diagram, because all the placket patterns, they remain same regardless of the twist angles and twist centers throughout the twisted regime. And it turns out there are two different regimes. The corner is the blue regions and the middle one is the yellow regions. So this yellow is the AB stacking regions and the corner is the blue stacking regions, and we can see that for the A stacking region all the square plackets are -1, and AB this is +1, and there are also some odd sided plackets, half of them are +I and half of them are -I. You can see for certain twist angles the pattern remains same for a particular twist center, and also if we change the twist center, still now my pattern is same. And also I am breaking the time difference symmetry, and so I am also getting some edge and corner localization, which is giving me a very beautiful patterns, and we can see different gapped and gapless spin liquid phases. So that is the summary. So we can see that this is a very tunable model we have proposed, and for the first ever exactly solvable bilayer models, where you can see different gapped and gapless spin liquid phase and also edge and corner modes appear, and we can see that generalized patterns of the ground state regardless of the twist angle, twist center. So I want to thank my collaborators, and this is published in peer review. Thank you.
Thank you. Any questions? So good afternoon everyone. Today I will be present our recent work on the correlation between metal to insulator transition and strain relaxation in NDNA3 thin films, which is a negative charge transfer insulator. So before going to that, we have to understand why these qualitative systems are this kind of nucleus showing insulator, but conventional band theory this is showing this should be a metal. So to look at that, we have to look at the first this Hubbard model. In the Hubbard model, first time is basically the hopping parameter, which is showing that how one electron from one side to another side this can move, and the U is on-site Coulomb repulsion. This on-site Coulomb repulsion, this is the energy required to put one electron on the same metal tension metal side. So you can see if this on-site Coulomb repulsion is less than the charge transfer insulator, that time the electrons will move from tension 3D to 3D. So if this charge transfer insulator U is greater than delta, that time that oxygen 2p orbital lies just below the Fermi level and above that 3D orbital. So that time the electron will move from oxygen 2p to 3D orbital directly. So this energy is a negative charge transfer insulator, but there is one more kind of charge transfer that is positive. If delta prime is less than 0, greater than 0, that time the ground state is D7. What happens that time if you want to move one electron from 2p to 3D, it is very unfavorable. So this can go this is not allowed to go from oxygen 2p to 3D, nickel 3D. But if this charge transfer is less than 0, negative charge transfer, that time the electron will move from oxygen 2p to 3D. That time one hole will create, ligand hole will create oxygen 2p side. That time the ground state is D8 L bar. So before transition, the metallicity is 3D7 and some fraction of 3D8 L bar. But after transition in the insulating phase, the fraction is 3D8 and 3D8 ligand, two ligand hole at oxygen side. So we can tune this kind of MIT of this kind of nucleates by various parameters, like by straining and by apply electric field also. If we change this rear side, ND side, that time also we can change tune the MIT of this kind of material. So in our case, we strain the material and change the MIT of the material. So for that we grow this material using passenger deposition. So for that we use those two kind of substrate. One is LAO, that is compressive strain, and another one is LSAT, that is tensile strain. So in the like LO and LSAT is cubic, and but NO is orthogonal. So now this will grow on LO and LSAT is diagonally. So for this compressive strain, this you can see this is a highly epitaxial grow on LO substrate 002 is going 004, NO is going 00. But one thing you can see, the outer plane lattice parameter is increasing with increasing thickness, but this is not a usual case for relaxation. We know that if it's grow, that time it will so decrease the outer plane lattice parameter. So to look at that, we did off-axis RSM. In off-axis RSM, you can see the in-plane lattice parameter of 1300 film is coherently like growing, but for 90 there is a gradient of in-plane lattice parameter. So let's see what happened like 5 to 1300, what is the like MIT of this material. So you can see for the 5 nanometer film, this is showing nice MIT around 110 Kelvin temperature, but for 3090 there is a upturn is there for 30 nanometer, which you can see in the inset that 30, but 90 is showing fully metallic. There is no metal to transition. So to look at we did head of STM of this 90 nanometer thick film. So we cut lamella from this, and then we go see that the like clear interface is there of LAO and NNO, lanthanum and LAO and NNO. So if you zoom this, that this is like clear interface of it. This is going NDNO3 nicely. On if you do thicker side, that time you can see that defined kind of region is there. One is you can see high contrast, is a low contrast image. So from there, if you zoom this area, you can see this is matching with a structure. This is not NDNiO3 structure. This is a structure of ND2NiO4, which is Ralston-Popper fault. Or this is a NDOM NiO2M minus 1, which is Ralston-Popper phase and a general formula. So we all know that how this is. If we grow a film on a substrate, that time when it's relaxed, it should going through some defects from the interface. But in our case, what happened? This is a normal relaxation. But in our case, see there is no defect at the certain thickness, around 10 to 12 nanometer. How you gonna see from the strain map? This is C outer plane lattice parameter strain map. From there you can see there is coherently strain from with substrate. There is no relaxation from the bottom or interface. So this is away from the thicker side. So to look at the local oxidation, we did yields. From yields you can know what is the thick, what is the oxidation of the this spectra is coming from the oxygen 1s2. This spectra is coming from electronic transition from oxygen 1s to oxygen 2p. If this peak is decreased, this is basically hybridized with oxygen 1s to 3d. If this peak is decreasing, means there is a change in oxygen nickel oxidation state. So how we can know that if we take position B peak and A peak, if substitute, that time you can see if this the difference will give my oxidation state. So you can see this around the perovskite region there is a 6.5 electron volt is that the distance between these two peaks, but for the defective region this is 5.7. So we can say there is a decrease of oxidation state, but for the strain case, this is showing opposite. This time, this is the outer plane lattice is decreasing with increasing thickness. Also, the coherently strain with for the 12 and 36 nanometer. You can see for the MIT of this is now MIT is changed. The MIT of this is now 140. Earlier it was 120. So to do that, we did head off, and you can see that now that defect is coming vertically through the region. And now we did same, and also outer plane lattice is showing the defect at the defective region. There is a variation of C lattice parameter. Now we deal that is in a different region. From there you can say this is a perovskite region. There is a clear 6.3 EV that distributed two peak, and in the defective region that is 5.5. So from here we can say that that's why the 36 nanometer that is film there is this fully metallic, and 6 and 12 there is this is clearly showing MIT. So in conclusion we can say that we grow. So you can also say that like for the up to 10 nanometer film, this strain relaxation is happening after that, and also the MIT is changed with respect to the strain film. One is for compressive is around 110, and for tensile now this is 140. Yes.
Thank you.
So
So how you determine the thickness?
we can determine by through XRR. XRR.
You didn't show, right?
Huh?
You didn't show the how.
No, we didn't. So this is XRR feed.
Right. Next.
Afternoon. I'm Sneha Shish. I'm a PhD student at IIT Kharagpur, and today I'm going to talk about the antiferromagnetic spin half trimer chain, and this work has been done with Professor Student2 Mondal. Though Professor Anup Bera and Professor Manoranjan Kumar has talked a lot about this trimer chain. However, I will be talking about the trimer chain from a fermionic perspective, and I will show some of the results where the fermionic perspective gives a better understanding of the results. So this is a brief outline of my talk. So I will first have a quick recap of the spin half chain, uniform chain, and then I will introduce the trimer chain and discuss my results. So the uniform chain, the Hamiltonian is simply this, and if you the ground state energy is given by the Bethe-Ansatz solution exactly this, and the excitation over the ground state the excitation of the ground state is a 2 spin-on continuum, and which is bounded by these two lines. So these results are important, and I will be referring to this result quite often. Now in the trimer chain, unlike the uniform chain, this here the exchange interaction changes in every third bond, and also there is a second nearest neighbor interaction within a trimer unit, and this has been experimentally realized in NCGO where the parameters are this. And some recently experiments have been done on this system, like INS experiment, and as well as DMRG and QMC calculations has also been done, and some interesting results have been found in this system, like 1/3 magnetization plateau and spin-on excitation and the higher energy doublet excitation and quarton excitations as they call it. Okay. Now, however, despite having these studies, there is no semi-analytical study on the trimer chain. Also, we wanted to obtain a ground state energy and low energy excitations analytically, and for the higher energy excitations we have done the mean field theory calculations, and from there we have actually explained all the experimental results that are there in the literature. Now the model we have taken is simply like this, and we have omitted the second nearest neighbor interaction within the trimer unit because for the sake of simplicity, and also for the very low value of the second nearest neighbor exchange interaction, it does not change the physics much. Okay, and the Hamiltonian is given like this, and the first part is the trimer Hamiltonian, and the second part is the trimer interaction part, and this where J2 is J2 by J1 is lesser than 1 here. Now, if you diagonalize this trimer Hamiltonian part, you get doubly degenerate ground state, and then the first excitation is also doubly degenerate, and then it is a quartet, and I am calling them as plus and minus, and it will be useful later on, and I am calling them D, capital D and Q. Now, as it turns out, if you calculate the effective low energy Hamiltonian, it turns out to be 4/9 J2. I mean, it is just a spin half antiferromagnetic chain Hamiltonian with a modified exchange interaction, and the factor is 4/9. And borrowing the result from the Bethe-Ansatz solution, you get the ground state energy like this, and the spin-on continuum that is bounded by this dispersion relation. And if you want to have a understanding of how the spin-on excitation is happening here pictorially, then you can actually map this. So, this is a spin-on excitation mechanism in spin half chain uniform, and you just simply replace these spin halves with the trimer SZ plus half plus minus half states, and you get the spin-on excitation for the spin trimer chain. And now since we now have the low energy physics, now we want to have the high energy physics, and for that we have to go to the mean field theory calculation, and for that we have done Jordan-Wigner transformation and Fourier transformation, and then Fourier transformation, and we have, and for the to deal with the 4 fermion parts, we have only considered the density channel, and the BCS channel is, I mean, this kind of terms are not appearing here, and we get a effective Hamiltonian like this, and we have solved it self consistently, and Ek alpha is basically the fermion bands that we are getting from here. And since there are it is a trimer system, so there are 3 sublattice degrees of freedom, and so we get 3 fermion bands, and thus ground state energy is something like this, and the ground state wave function is I mean, since it is a half filled state, so you just keep on filling up to the half number of state, and then this is for 0.2 gamma and this is for 0.5, and the ground state calculated from here is actually 2 to 4% from the Bethe-Ansatz ground state energy. So, that is quite close that we are getting even from the mean field. So, now that actually encourages us to go for look for the higher energy excitations, and that we have done by calculating dynamical spin structure factor. And as you can see here, so this is the dynamical spin structure obtained from the DMRG, and you see these are quite similar, and this lower spin-on band, so the bound are given like this 0.32 J1, 0.61, this number is actually within 10% margin of the what we are getting from the Bethe-Ansatz I mean effective low energy Hamiltonian value. So, that is quite close and encouraging, and also now to have an understanding how the bands are coming. So, this spin-on band, so this is actually the excitation within the middle band, that is it is going from here and sitting on the unoccupied state, and the middle band is from the bottom to the middle and middle to the top, and the upper band is basically from the bottom to the top. Now, we have also calculated magnetic and thermodynamic responses, and then they have got 1/3 magnetization Plato from the experiments as well as from the DMRG, and as you can see here we are exactly getting that 1/3 magnetization. This is also obvious from the Oshikawa Yamanaka Affleck criteria. Anyway, so that we are also getting, and to have a sense of why this Plato is forming there, 1/3 Plato. So, that you can think of as because these 2 bands out of the 3 is being filled here. So, if you calculate the magnetization, you get 1/3. And also we have calculated magnetic susceptibility, which is varies as 1/T in the higher temperature, and in the low temperature we get a peak, and this peak we have seen this is also matching quite well with the experimental value as well as the theoretical the DMRG and all the other calculations. And also we have performed the specific heat calculations, and the specific heat is also, I mean, in experiment in Yasui 2014 they have showed this lower peak which is actually matching with our calculation. However, they have not shown this peak, and we are predicting this peak. If someone do the experiment at higher temperatures, they might get this peak. So, this is our prediction. So, that is it. So, we have actually done the theory where the low energy as well as the higher energy physics is described quite well, and there is another compound which is in the other limit where J2 by J1 is greater than 1. So, that can also be studied with this model, and other Rix and Raman intensity can also be studied. Thank you.
Thank you.
Okay. Hi, good evening everyone. First of all, I would like to thank the organizer for giving us all an opportunity to speak here. My name is Barkha and I am working as a PhD scholar with Professor Yogesh Singh at IISER Mohali. So here I am going to present one of my work titled Magnetic Frustration in an ytterbium based triangular lattice selenide. So this is how basically I have organized my talk for a better understanding. First of all, I'll start by giving an introduction. So magnetic frustration refers to the competing interactions present in the system which prevents it from attaining the conventional magnetic order. So in daily to daily life, frustration comes from an emotional response of being blocked or stuck from some in some or the other kind of way. But sometimes a little frustration can make our life interesting too, and similar happens in physics as well, where it lead to a highly entangled magnetic ground state with exotic excitation known as the spin liquid. Historically, triangular antiferromagnets were the first system on which the idea of quantum spin liquid was established by Philip Anderson, who coined the term resonance valence bonds, which means two spins on the neighboring side can exist simultaneously into two configurations, and the quantum superposition of this state is termed as a spin singlet. So, what is the route to realize this kind of a state? It's by generating quantum fluctuation. And recipe for quantum fluctuation is definitely low dimensionality, low spin, geometric frustration. In fact, most of the spin liquid are spin half quasi low dimensional magnet with antiferromagnetic exchange. So quite recently, this rare earth based, especially ytterbium based chalcogenide family has emerged as a promising platform for holding quantum spin liquid candidates. One of the reasons is because of its crystal structure, which consists of a perfect triangular lattice layers separated by the non-magnetic ions. And second interesting point is the presence of the strong spin orbit coupling and the effect of crystal field effect, which allows the system to be treated as an effective spin half system due to the formation of the Kramer's doublet. So all these features make this an interesting platform for holding quantum magnetism. This is a reference image showing the ytterbium 3+ ion splitting in D3D symmetry by spin orbit coupling and then crystal electric field effect, which leads to the formation of the Kramer's doublets. So ytterbium, magnesium, gallium, oxygen was a first discovered rare earth or ytterbium based frustrated magnetic system showing the signatures proximate to the quantum spin liquid line. However, due to the presence of the intrinsic side disorder between magnesium and gallium, it leads to the search of the cleaner system or leads to the emergence of this ytterbium based family AYB-Se2, where A is a monovalent cation. So depending upon the size of the A cation or the metal chalcogen chemistry, basically this exhibits different crystal structure or space group and have a variety of magnetic properties. Out of these, sodium ytterbium selenide has been the most extensively studied as a promising quantum spin liquid candidates, and till date no long range ordering has been found down to the lowest temperature measured. Although potassium and cesium ytterbium selenide are reported to order at around 0.3 and 0.4 Kelvin temperature scale by neutron diffraction data, in spite of exhibiting the broad continuum excitation spectrum in inelastic neutron scattering data. Various other field induced and various interesting magnetic properties have also been observed for this compound at low temperature and high field. So, the magnetic behavior of all these triangular antiferromagnets can be explained by the J1 J2 model, where J1 and J2 refers to the first nearest and second nearest neighbor interaction. And this particular work by A.O. Shai demonstrated that this J2 by J1 ratio can actually be linked to the size of the cation A. So he demonstrated that as we move up towards the periodic table, the size of the cation decreases and the J2 by J1 ratio is pushed towards the limit, which falls in the quantum spin liquid regime. So going by the ionic size, copper has a smaller size as compared to sodium. So it motivates us to explore the properties of copper ytterbium selenide. And the another key motivation is because of its structure, which is shown here. As we can see, it consists of the perfect layers of triangular ytterbium ion, which is separated by along the C axis by copper selenium tetrahedra. To confirm that copper does not contribute to the magnetism, we have also done the XPS, and the XPS confirms the presence of the copper 1 plus valence state. Other characterization techniques like powder XRD, single crystal XRD, EDX techniques have also been done to confirm the phase purity. Now I will present some of the preliminary data that I have taken. So the resistivity data includes the insulating character, confirming the localized nature of the ytterbium movements. The magnetic susceptibility data did not show any long range ordering despite the presence of strong antiferromagnetic exchange interaction, which is equal to -70. There was no signature of any spin freezing as well in the ZFCFC data. In the heat capacity data, there was no indication of any sharp lambda type anomaly. Instead, a broad hump-like feature in C magnetic, which has been obtained by subtracting the lattice part, taking copper lutetium selenide as the reference. This broad hump-like feature is actually similar to what has been observed in the other members of this family, and it may be due to the presence of the short range correlation that are being developing. Now, at low temperature, the crystal electric field effect leads to the formation of the Kramer's doublet, which is indicated by the reduced value of the moment that we obtain at low temperature, which correspond to the value of the spin half, whatever we expect for the spin half, and also the entropy recovered to RLN2 around 50 Kelvin, which corresponds to the value of the entropy that is recovered for spin half. So we can safely say that at low temperature, the system behaves as a J effective half spin system. Anisotropic measurements on single crystals have also been done. Clear, although weak, anisotropy can be seen in both the MT and MH data. No saturation has been obtained till 9 Tesla, and the moment only reaches 0.7 mu B. The value of the G tensor and the value of the theta, which indicates the exchange interaction, is larger in plane. So we can say that the interaction in plane is larger as compared to the C axis, which is also consistent with the results of whatever has been observed in the other members of this family. So I can say after all these results that it provides another interesting platform to realize a quantum spin liquid regime. Preliminary data has also been already been published in PRB, and the work that is in progress or can be done are thermal conductivity measurement to explore the excitation, crystal field excitation study to establish the J effective half picture, and high pressure measurements can also be done to place this compound in where it lies in the J1 J2 phase diagram. So thank you so much for your so a lot of work has been going on, and 4 of the papers in spite of mine has been published. So I would like to thank my collaborator, and thank you so much for your attention.
So, good evening everyone. I am Subramaniam, a final year PhD student in ISER Bhopal. I am going to talk about anomaly induced hybrid electromagnetic mode in wild semimetals, which is our recent work in collaboration with Dr. Suhas Gangadharya, who is my supervisor, and Professor Eugene Mischenko. So, I will give a brief introduction and motivate the problem, and then I will discuss the framework to solve this problem, and then discuss our result, which is anomaly induced hybrid electromagnetic mode, and I will conclude with a quick summary and future direction. So, this would be the outline of the talk. So, yeah. So, the wild semimetals are 3-dimensional topological materials in which pair of non-degenerate bands cross linearly at isolated points. So, this low energy Hamiltonian at the isolated points resembles the Weil equation describing the massless chiral fermions. Hence, we call these isolated points as Weil nodes, and existence of these Weil nodes require either a breaking of time reversal symmetry or inversion symmetry, which leads to a non-zero Berry curvature around the Weil nodes. And Weil nodes acts as a source and sink of the Berry curvature in the momentum space. So, one of the striking feature of wild semimetal is chiral anomaly, which is the non-conservation of chiral charge in presence of the parallel electric and magnetic field, which is manifested in wild semimetal as charge pumping between the Weil nodes of opposite chirality, or there is a chemical potential imbalance created which is proportional to parallel electric and magnetic field. This is chiral anomaly in wild semi-metal. So the resulting chiral chemical potential imbalance generates a current along the magnetic field, which is known as chiral magnetic effect. And yeah, before going to the next slide, so we can see the electromagnetic response is highly modified by the chiral anomaly and chiral magnetic effect in the wild semi-metals. See, one of the natural question to ask is how the bulk electromagnetic modes in wild semi-metal is affected by the chiral anomaly and chiral magnetic effect. So in the metals and wild semi-metals, we have three bulk electromagnetic modes. So in metals, we have a longitudinal plasmon mode and a transverse plasmon polaryton modes. And in doped wild semi-metal, the bulk electromagnetic modes does not have a longitudinal transverse section. It just gets mixed and becomes anisotropic due to the wild node separation vector B, which has already been done by Francisco Pellegrino and others in 2015. So one of the central question what we ask is how the chiral anomaly and chiral magnetic effect affect the bulk electromagnetic modes in wild semi-metal. For this, we have a varying electromagnetic field having frequency omega and propagating along y direction q, and we have applied a static magnetic field B naught, which is classically weak such that Landau quantization is neglected. So here, due to this varying electric field and a static magnetic field, we are going to activate chiral anomaly, but since the electromagnetic field is varying, there will be oscillations in the chemical potential imbalance, like we are showing at time t. This is what happens. The chemical potential goes here and here it goes, and then after a time t dash, it follows here and this goes here. So it starts to oscillate. So what we ask is how do these oscillations in chiral chemical potential imbalance affect the bulk electromagnetic modes? To answer this question, we developed the following theoretical framework where we use semi-classical Boltzmann formalism to solve coupled Maxwell's equation and Boltzmann equation self-consistently. Yeah. So we write the Maxwell's equation for the bulk of wild semi-metal, and we see the Maxwell's equation becomes inhomogeneous, and in order to solve this right hand side, we use Boltzmann equation and obtain this right hand side in terms of electric field again, and then we plug it back to get the overall Maxwell equation, and we can see the Maxwell's equation is now captured the chiral anomaly and chiral magnetic effect, and then we solve the system to get our results. So initially we had a bulk plasmon mode in both parallel and perpendicular configuration, where parallel and perpendicular configuration is corresponding to the wild node separation vector parallel to the propagation of the electromagnetic wave, or wild node separation vector perpendicular to the propagation of electromagnetic wave. This is the two configuration because the wild semi-metals electromagnetic mode is anisotropic. So we get a new mode because of this chiral density oscillations and at low energy, which is linear, and then it starts a avoided level crossing or level repulsion with the existing plasmon mode, and we call and hence we coin this as anomaly induced hybrid electromagnetic mode. So we can see the anomaly induced hybrid electromagnetic mode is highly dependent on theta, where theta is the angle between magnetic field and the wave vector. So when theta is pi by 2, that is when the applied magnetic field does not have a component along the wave vector, then we cannot have the bulk mode, the anomaly induced hybrid electromagnetic mode vanishes, and hence the hybridization. But when we have a component of magnetic field along the wave vector, so we observe this anomaly induced linear mode, which can be detected easily in experimentally using electron loss spectroscopy. So now this is the modes, but in order to study the damping of these modes, how robust the modes are, we plot the loss function, which is the negative of imaginary part of the inverse of dielectric function. So here the red dots represent the solutions of Maxwell's equation, is the modes, but we can see the blue peak here, peak represents the existence of this mode which survives the damping. So in perpendicular configuration, for any arbitrary angle of theta between 0 and pi by 2, we can the mode survive the damping, but whereas in parallel configuration, the modes vanish, does not survive the damping for any angle, arbitrary angle between theta 0 to 90, but at exactly when theta is 0, that is when exactly the applied magnetic field is along the is parallel to the wave vector, the modes are robust and survives the damping. So this is our result. So I will summarize the talk. So what we ask is, due to the varying electric field and a parallel static magnetic field, there is an oscillations in the chiral chemical potential imbalance because of the chiral anomaly. And due to that, we uncover an previously unidentified anomaly induced hybrid electromagnetic mode, which emerges due to the hybridization of the charge density oscillation, which is plasmon oscillation, and then the chiral charge density oscillation because of the chiral anomaly. So, and the existence of and damping of this mode are strongly controlled by the magnetic field orientation, reflecting its anomaly induced origin and providing a distinct experimental signature of chiral anomaly physics in wild semimetals. So, one of the future direction is, so in tilted wild semimetal, how would the tilt affect this hybrid bulk electromagnetic mode? Yeah. Thank you for your attention. Yeah. And you can scan the QR for the article, it's in PRB. It's okay.
Okay, so first of all, thank you organizers for this opportunity. So my name is Kiran and I'm from Rama Research Institute, Bangalore. I'm a PhD student there and I'm working with Professor Dipendra Rai. So the title of my talk is the many body winding from Pancharatham geometry. So this talk is going to be based on part of our recent work which is available on archive on this link. So if you are interested, please go and have a look at it. Okay, so let me start by the SSH model, Sush-Rifer-Heger model. I don't think I need to introduce this model to this audience, but still let me just say that the SSH model is a bipartite model, tight binding model. So it has sublattices A and B, and there are these staggered hoppings V and W like that, and this is the Hamiltonian of the model. So this is the non-interacting version of the model, and this supports topologically trivial and non-trivial phases characterized by winding number 0 and 1, and it satisfies something called bulk boundary correspondence, which states that the number of edge states in the open boundary conditions are related to the bulk topological invariant. So now our goal is to find out what happens to this bulk boundary correspondence when we add interactions in this model. So the way the interactions are added are like this. So we add just like the hoppings, we also allow the interactions to be, so the interactions are nearest neighbor interactions, but they are also staggered. So within the unit cell the interaction strength is U, and between the unit cell the interaction strength is capital V. So now since we have gone into an interacting problem, we need to have some kind of some version of the bulk invariant for many body states. So to do that we apply periodic boundary conditions along with this phase e to the I phi, and this particular boundary condition now is known as twisted boundary conditions, and this for angle phi is known as the twist angle. And this is now the interacting Hamiltonian along with the twist angle phi, so it depends on this angle phi. Now this twisted boundary condition is equivalent to having a closed loop that is made out of this SSH chain and having this magnetic flux phi being passed to this closed loop. Now to calculate this many body topological invariant, which is the many body Berry phase, we vary this magnetic flux phi from 0 to 2 pi, and for computational purposes it can be discretized into some n phi number of divisions, and at each phi value you diagonalize the Hamiltonian, find out the ground state g phi, and in terms of those ground state the many body Berry phase is given by this formula over here. Now this is the discrete formula. Now it can be, you can take a continuous limit and get the many body Berry phase formula in this continuous limit like this. So there are two terms. The first term is the integral of Berry connection A phi, which is given by this expression, and the second term is the argument of the overlap between the initial ground state and the final ground state. Now this also the many body Berry phase for half filled case, even in the non-interacting case, gives two phases characterized by gamma equal to 0 and gamma equal to pi. Okay, so now it turns out that we can generalize this model. We can introduce this longer edge hopping, which is denoted by T over here, between sublattices A and B. Now what this does is it gives rise to higher winding number topological phases. For example, in this particular model with this Hamiltonian, along with hoppings V, W and T, you get phases with winding numbers 0, 1 and 2. So now we have, because of this T hopping, we have my phase with winding number 2, and which can be calculated using block Hamiltonian in the non-interacting case. So let's see how the winding number looks like. So here I am plotting the winding number calculated from block Hamiltonian in the first part, and in the second part I am plotting the many body Berry phase. So as T parameter is varied, the winding number says that there are phases characterized by winding number 1, 0 and 2, but the Berry phase shows that there are phases characterized by gamma equal to pi and 0. So it cannot distinguish between the phase characterized by winding number 0 and winding number 2. Now why this is happening is, since Berry phase is a phase, it is a complex phase, it is only defined modulo 2 pi, so it cannot differentiate between winding number 0, 2, 4 and like that, as well as it cannot differentiate between winding number 1, 3, 5 and like that. So this is a limitation of the Berry phase, many body Berry phase, so we need to overcome this. So to do that, we define something called Pancharatam's winding number based on ideas similar to Pancharatam's ideas. So what we do is, we have this periodic twisted boundary condition. We have Hamiltonians as a function of phi, we have the ground state as a function of phi, as phi changes from 0 to 2 pi. Now what we do is, we fixed a ground state at phi equal to 0 to be our reference state. And now at each phi, we take this Pancharatam's triangle, which consists of these 3 states. So one of the state is always going to be our reference state, and the other 2 states are the ground state at the given phi and the ground state at the adjacent phi. Now from this triangle, you define this Bargmann overlap B phi like this. So there are 3 overlaps. The first one is the overlap of ground state reference with the reference state with G phi with G phi plus 1 and G phi plus 1 and again reference state. Now denoting the phase of this B phi as theta j, we sum over all these theta j's and divide it by pi and denote this quantity as Pancharatam's winding number. Now this is the winding number that we have defined. Now if we can take the continuous limit of this as well. And to do that, we define the argument of the overlap of G phi with the reference state to be chi phi, and in terms of this chi phi, the continuous limit of the winding number gives you this expression. So again there are these 2 terms. The first term is the same as the Berry phase term, this is the Berry connection, but the second term has this derivative of this chi phi that we have defined. Now it is easy to see that this formula is gauge invariant. So to do that, we can take gauge transformation. So under G phi going to e to the alpha phi G phi, it can be shown that the a phi goes to a phi minus d alpha by d phi, where alpha is the gauge transformation, and the d chi d phi terms goes to d chi d phi plus d alpha by d phi. And since in the expression for winding number, Pancharatam's winding number, a phi and d chi d phi, the summation appears, the alpha terms, the gauge dependent terms cancels, and the nu remains invariant under this gauge transformation. Now let us compare the Pancharatam's winding formula with the Berry phase formula. Now if you look at these 2 formulas carefully, you will realize that apart from these 1 over pi factors, the only difference between the 2 formulas is this second terms. So the Berry phase only cares about what is the relative phase difference between the initial and final state. So it does not care about how the final state evolved at that state as we varied phi from 0 to 2 pi, but it could have happened that along this evolution from 0 to 2 pi, the state might have undergone multiple windings with respect to the initial state, which is completely ignored in the Berry phase formulation. So and that is exactly being kept track of in this integral of derivative of d chi d phi terms. So that is the difference, and that's why this Pancharatam's winding number keeps track of all integer winding numbers and can resolve between all the integer winding numbers. So let's see under what conditions this is quantized. So if you add a generic disorder, the winding number is not quantized, but if I add the disorder in a symmetric invariant manner way, if I add it in a such a way that the inversion symmetry is satisfied, then it is quantized again. And this can be understood in terms of inversion symmetry analytically. For example, h phi under inversion goes to h of minus phi, and under complex conjugation again h phi goes to h of minus phi. So we can combine these 2 symmetries, inversion and the complex conjugation, to form an anti-unitary symmetry A equal to pk, which commutes with the Hamiltonian. And now this anti-unitary symmetry, it can be shown that it leads to the fact that this B phi, which was used in defining the Pancharatam's winding number, is a real quantity. So because of this anti-unitary symmetry commuting with the Hamiltonian, B phi is real, and since real numbers can only have phases 0 and pi, and we are summing over these phases, the Pancharatam's winding number is always going to be quantized as long as the Hamiltonian satisfies this anti-unitary symmetry. So now an important point here is that the inversion symmetry is playing the role, but it need not be an inversion symmetry. We just need some anti-unitary symmetry commuting with the Hamiltonian for the quantization of the Pancharatam's winding number. Okay, so how much time do I have?
So only 2 minutes.
Okay, so this was about the Pancharatam's winding number. So our bigger goal was to establish or to study the bulk boundary correspondence in interacting systems. So we defined a bulk invariant. Now we need something to characterize the edge physics. So this is the quantity which was defined by Lee and Halden in this 2008 PRL paper. So entanglement spectrum is nothing but it's simply the eigenstates of the reduced density matrix of some part of the systems. You take periodic boundary condition, you trace out half of the degrees of freedom, and you diagonalize the remaining the density matrix of the remaining system. So here is the results. Here is the main result. So the first one is the Pancharatnam's winding phase, winding number phase diagram. So there are these 3 phases characterized by winding number 0, 1 and 2, and these 3 are the lowest 32 levels of the entanglement spectrum. So you see that in the trivial phase, the lowest level is non-degenerate. In the winding number 1 phase, the lowest level is 4-fold degenerate, and in winding number 2 phase it is 16-fold degenerate. There are 16 of these here. So there is this quantitative relation that the lowest lying entanglement spectrum level has 4 to the nu fold degeneracy, where nu is the bulk winding invariant, and this is the quantitative statement of the bulk boundary correspondence for the interacting system. So I would summarize. Before that, I would just like to acknowledge my PhD advisor, Professor Dibyendu Roy, and I will just keep this slide here and take any questions if there are any. And thank you for your kind attention.
Thank you. Any question?
We have done with Professor Darshan Joshi. So what is photonic spin Hall shift? So basically, if you have a linearly polarized light and it incident on a plane, then after incidenting it gets splitted into left and right circularly polarized, left and right circularly polarized light, and it gets shifted from the center. So you can see this is the shift for plus circularly and this is the shift for minus circularly polarized light. This basically happens because if your linearly polarized light is composed of few wave vectors, then each wave vectors is following different boundary condition. So according to that, after reflection, each of its polarization vector traces a closed loop in the polarization space, momentum space, which gives you the real space shift. And this is not only a theoretical phenomena, experimentally also you can see these 2 distinct beam spots. You can find the details in this paper. So, and the spin for left and right circularly polarized light is related to the Fresnel's coefficient, that RPP, RSS, RSP, like this, and this Fresnel's coefficient are basically the function of the conductivity, which has the information about the topology. So far people have been trying to distinguish between different topological phases with this plus and minus circularly polarized shift, but I mean using that delta y plus minus h shift, but people could not find a signature remark to distinguish between those phases. So then we tried to define centroid shift in this quantity, which is basically the intensity weighted average of the plus and minus circularly polarized shift. So here we will show you that we can using our definition of centroid shift, we can actually distinguish between different kind of band topological phases. So here we have connected our results, that centroid shift through Fresnel's coefficient, through conductivity, where you can see although this looks very complicated, the denominator is very big, but I will show you that this denominator will not analysis the topology, but this numerator, that smaller part, but only using that numerator we can distinguish between topological phases. So what is our objectives? So our question was that can we probe band topological phases using this PSHE as a probe. We have checked this for 2 system, 2D system Halden model and 3D system, 2 cases, gapless and gapped phases, and we will show each phase that we actually can distinguish this. So this is a brief overview of Halden model. Of course you all know it. So this is basically a graphene Hamiltonian with 2 different sublattice A and B. So this first term is nearest neighbor hopping,
and the second term is consist of next nearest neighbor hopping with a complex phase factor in a clockwise direction, and the last term is the onset chemical potential. And we can also write the low energy Hamiltonian around the Dirac, where we know the Dirac point appears, that high symmetry point k prime in Brillouin zone, and that last term delta tau, which is responsible for opening the gap in the system at k prime point. So here from the Halden phase diagram, I will just say one thing, that if that delta, that mass term has the same sign, then it is in topology trivial phase, but if it has the different sign around two different values of graphene, then it is in the topological phase with charge number 1 and -1. So our goal is to distinguish between this trivial versus charge insulator phase with by seeing the centroid shift behavior. So we have calculated the optical conductivity for that Halden model, and here you can see that this is the expression for longitudinal conductivity, real and imaginary part, and this is for the Hall conductivity, real and imaginary part. And if you see from the expression, also from the plot, that if I am in topological or in trivial phase, that longitudinal conductivities does not depend on the sign change of delta tau, as it always in delta tau square or mod of delta tau. But if you look at the Hall conductivity expression, then you can see that it has a direct dependency of the sign of tau multiplied by delta tau. So if we are in trivial phase, then the sign of Hall conductivity will always change, but the if we are in topological phase, then the sign of Hall conductivity, both real and imaginary, will never change. And then we have done the calculation for our definition, using our definition of centroid shift, where I have written this, that longitudinal conductivity is same for both phases and it has a fixed sign structure, and for trivial phase, as this Hall conductivity changes sign, so you can see that this numerator will have a zero crossing if we are in trivial phase. So here you can see the centroid shift plotted as a function of energy, and there is a sign change from positive to negative. And if we are in topological phase, along with the longitudinal conductivity, the Hall conductivity also has a specific sign structure for charge number 1 or -1. So if you put that condition all together in the n of theta, then you can see that the sign of photonic spin Hall shift will never change sign, and particularly for charge number 1 it will always be negative, and for charge number -1 it will always be positive. So that is how we can detect topological versus trivial phase for charge insulator model, and we have also done that for 3D topological system. So here I am just flashing the results, I will not go into detail. So here for while semi-metal phase, you can see the centroid shift we have plotted, that is always negative, whereas for same gapless system Dirac semi-metal, by annihilating the while semi-metal point, it is basically 0. And again we have done the same thing for 3D, two different topological phases, quantum anomalous Hall versus normal insulator. Here you can see if we are in QAH phase, that is a topological phase, here it is always negative, but if we are in trivial phase, that is normal insulator phase, you can see there is sign change here. So in summary, I can say if we are in topological phase, then there will be no sign change, but if we are in trivial phase, then it centroid shift either will be 0 or there will be a sign change. So a easy experimental protocol can be done based on our result, where no full frequency scan is needed. Only if you look at the sign of the centroid shift at low frequency and at the high frequency, it will reveal the topology. And we also like to, for future work, we would like to use our non-invasive measurement for different kind of detecting different kind of phases of matter.
Thank you again. And there are two.
I am working with Professor Kaushik Pal. So today I will be discussing the topological phase diagram of non-magnetic half-Heusler compounds. So this will be the brief outline of my talk. I will be explaining the difference between trivial and non-trivial topological insulators, and then I will describe topological Dirac semimetals, and then I will describe the compound which I am working on. Then I will explain the strain engineering in our half-Osler compound LiMgBi, and at last I will conclude the talk with the topological phase diagram of LiMgBi. So let's start with the trivial and topological insulator. As we know that topological insulator are insulating in bulk, but they conduct electricity at the surface. That means they possess metallic surface states. This happens because of the topology of electronic wave functions in the bulk of the material. For example, we are taking two compounds, antimony selenide and bismuth selenide. They both have same crystal structure, but still this compound is trivial, but the another one is topological insulator. So the difference lies in the band inversion. At gamma point, band inversion happens in this case. This is because of the large spin orbit coupling coming from the bismuth atom. And now due to the bulk boundary correspondence principle, so due to the bulk boundary correspondence principle in trivial insulator, there are no surface states are present, while in the topological insulators there are surface states present in the bulk band gap of the material. So how can we differentiate between trivial and topological insulator? We can differentiate using the Z2 invariant. So in topological insulator, due to the band inversion, in normal insulator, the conduction band is derived from the s orbitals, and the valence bands are derived from the p orbitals, while in the topological insulator band inversion has happened. That is why the parity eigenvalues has inversed. So if the system possesses inversion symmetry, we calculate Z2 invariant using this formula. What we do is we calculate the parity eigenvalues at all the trim points and all the occupied bands, and using this formula we get to know if our material is topological or regular insulator. So if it is 1, it will be topological, otherwise it will be regular. So for example, here this is the 2D trim plane, and band inversion happens at the gamma point, and this gives the strong topological index to be 1. While in this 3D TI, again band inversion has happened at this point, so the topological index is 1 here. Now we also study topological semi-metal phase. In the topological semi-metal phase, we mostly study the Dirac semi-metal. In Dirac semi-metal, there is no gapped state present. Instead, there are two bulk Dirac cones present in the axis of rotational symmetry axis, and they are protected by the rotational symmetry of the compound. And the key feature is at the surface they form Fermi arcs, and these Fermi arcs, they connect the projections of these two bulk Dirac nodes. Experimentally, using the RPS method, people